Hello? Okay. This is the 16A CSM mini lecture on projections. So first we'll go over what vector projections are, and then we'll go over one question from a previous exam. So from here, we see that this is read as the projection of U onto V is equal to the dot product between the dot product of U and V divided by the norm of V squared times the vector V. One way I like to think about this to help remember how to read this here would be that U is bigger than V, so V is almost like a subscript. So it's like U is casting itself onto V. So from the picture here, we can also think of vector projections as the shadow of the vector U, which is what it looks to be the bigger vector, like size-wise, not the actual vector, over the vector V, which is almost like a subscript here, how we write it. So we can derive the formula for the projection of U over V. So we should keep in mind that cosine theta is equal to the dot product of U and V over the norm of U times the norm of V. Or alternatively, you could also write it as the norm of U times the norm of V times cosine theta is equal to the dot product of U and V. So if we take this right triangle here and denote this angle here theta, since we denoted this angle theta, we know that cosine theta is the adjacent scalar over the hypotenuse scalar. So we have that cosine theta is equal to the scalar of the projection of U over V. And then over the scalar of the U vector, or which would be the norm, or like the magnitude of this vector. So we can just write it as this. But also keep in mind from earlier here, where we know that cosine theta is equal to the dot product of U and V over the norm of U and V multiplied together. So if we sub that in, we get that. And this bracket notation is just another notation for denoting the dot product. We can also multiply this out such that if we multiply each side by the norm of the vector U, we can cancel this out so that we have the dot product of the U vector, the V, and the V vector over the norm of the V vector. And also keep in mind that the norm of a vector is basically the magnitude. So if you were to take the norm of vector V, it would essentially be V1 squared plus all the components of that vector, and then you take its square root. But keep in mind that this quantity here keep in mind that this quantity here where the scalar of the projection of u onto v is still simply just the scalar. So you'll notice that this dot product here will give you a scalar, and then the norm of v will also give you a scalar. But this gives us the important question of how can we turn this into a vector, since we want to find what is the projection of u onto v. Keep in mind that the projection of u onto v lies in the direction of v, or the vector that's being the vector that's being casted on. So we see that the projection of u onto v, so v is the vector v is what's being casted on right now. So what we want to do is to convert this quantity here into a vector is to multiply this quantity by a unit vector that lies in the direction v. So we get that vector v over the norm of v. And this is something called normalization, where the magnitude of this vector is now 1. So as an example, let's suppose that v is equal to 1, 1. So if we take the norm of v, it's 1 squared plus 1 squared, and then we take the square root of this. So the norm of the vector v is equal to the square root of 2. And if we want to normalize this vector, we simply do the vector v divided by its norm. So we get that this quantity here is now 1 over square root 2 for both of its numbers. So if we take its norm again, so the norm of vector v over its norm, if we square both of these, if we square both of these numbers and then we take its square root, we see that equal to 1, meaning that the magnitude of this unit vector, which we can also alternatively denote q, is equal to 1. So the intuition behind this, why we multiply by the normalized vector of v, which is the vector that it's being casted on, is so that since we have this scalar, we want the projection of u onto v to lie in the direction of v. So this vector here will be in the direction of v. So if you can see visually from this example here, 1, 1 would lie in this, would look something like that. And then 1 over square root 2 would probably look like something like this. So they are going in the same direction, but their magnitudes are different. And you want to multiply by magnitude of 1, since you already have this scalar right here. So now we've derived our formula for the projection of u onto v. So moving on, we're going to be doing the 2020 final exam, question 8D. So you're given these three plots, P1 through P3, with the corresponding vectors V1 through V3. So we want to choose the option that correctly expresses V1 as either the vector B or the projection of B onto the vector A, or B minus projection of vector B onto vector A. So from the options here, we see that the only option, or sorry, never mind. So visually, we see that for plot P2, that V2, the vector V2 is simply just the vector B. So if we take a look at our options, we said B is not an option because V2 is expressed as a projection of B onto A. C is also not an option. E is also not an option, and F is also not an option. So now we're narrowing it down between A and D. So the difference between A and D is that it's naming V1 as a projection of B onto A, while vector V3 is equal to the vector B minus the projection of B onto A. So this is flipped from the format that we used earlier, but if we do flip it, we see that V1 is a scaled version of vector A. And usually that means that A is the vector that's being casted on. So by process of elimination, our answer is going to be option A. But to also explain option V for the third option for plot 3 for vector V3. If we draw this out again, so vector A, vector B, and then vector V3, if we move this vector here, if we move vector V3 in between A and B, this is not drawn super well. We see that simply that this vector V3 is also has the same magnitude as this vector here that goes from the vector B to the vector A. So if we just flip this, so it's like how we did here, so we can better visualize this. We see that vector V3 is just this vector right here. So since we know that this vector here was the projection of B onto A, I think that via vector addition subtraction, we know that projection of B onto A plus vector V3 is equal to vector B. So if we were to isolate vector V3, we would get it's equal to the vector B minus projection of B onto A. And then that's exactly what we have here. So we also see that this vector V3 here is orthogonal to the projection of B onto A, and orthogonal simply means that it's at a right angle to this vector. But this was the walkthrough, or not walkthrough, like a mini lecture for projections for CSM 16A, and a tiny walkthrough of this question on the spring 2020 final exam number 8.